We are so quiet. You guys have learned my trick that I don't tell you that we have actually been live for about 30 seconds now. Yeah, this trick is getting old. I have to come up with a new trick. Hi everyone, thanks for joining us today. We're having a very fun conversation about physics and machine learning. I have with myself my awesome co-host Serena, as well as Adrian and Thomas. I'm going to ask Adrian and Thomas to introduce yourselves very quickly for our audience. Adrian?
Okay, I'll go first. My name is Adrian Perez Galvan, and a few lifetimes ago, I used to be a nuclear physicist, an atomic physicist, but now I do data science in a company doing early research drug discovery.
Awesome.
And I'm Thomas Kleberg. I'm a senior data scientist at Shopify. I'm working on projects to help merchants find more customers. We use a lot of ML in various incarnations. So in the past lives, I've worked in finance, financial services, insurance, e-commerce, and technology as well. So a lot of different applications of the same kind of things.
Very cool. Adrian, sometimes I joke with people and I say I became a data scientist like a good physicist. So a lot of us do that. So What are you all drinking? I'm drinking time tea with a bit of twist. I had a bit of coffee left in my cup and I just poured the tea on it. So it's a coffee-induced time tea.
I think they call that it would be a dirty time. Like dirty chai is a popular drink.
Interesting. Okay. Do you have to have like milk or cream or something to make it dirty, or you just?
It's the coffee.
The
shot of espresso, I think.
Yeah, I think it's typically a shot of espresso. So yours is more like a watered down, a muddy time.
I'm on giant mug of black coffee. That's where I like to sit in the morning. You can move to tea in the afternoon. Yeah.
Yeah. All right.
For me, unfortunately, just plain water.
Water. Healthy.
Boring plain water. Yeah.
Yeah, me too, Adrian. I've just got a big, so kind of a mix of Thomas and Adrian, just a big mug of hot water. Actually, I have two. So, yeah.
You don't want to move, eh?
No.
So what's new with you, Serena?
Well, as some of you may or may not know, I'm the sole developer of a vegan app called Food Shake, and recently I added a feature called a baking calculator, which I may or may not have gotten inspiration from a pseudo competitor. So this calculator tells you how to convert n number of eggs to n tablespoons of whatever substitute takes care of the scaling and the substitutions. And I got some feedback from users already that's quite positive, which is great. But I'm always sort of struggling to get negative feedback because I feel like people are too nice to me, so it doesn't really help me too much. But yeah, that's what's new.
Awesome. So today we are here to talk about physics and reinforcement learning. That brings back my old world and new world. I guess same with Adrian. So I'm very excited. What's that?
Good memories.
Good memories, exactly. I do actually miss physics days whenever I see papers like this. And I'm like, I should definitely sit down and read this carefully, but then I'm always very lazy. So I find people like Adrian, Thomas, and Serena to talk about the paper and learn from them. So on that topic, Serena, you had a bunch of questions to ask to get us started.
Yes. So I thought I would share my summary of the paper and why it's important, because this topic of nuclear fusion, beyond my few undergrad courses in chemistry, it's all very new to me, and I've forgotten a lot because it's been a while since then now, which makes me feel old. But anyways, so setting the stage. So on February 16th, 2022, an article came out in Technology Review talking about DeepMind's work. And the article is titled, DeepMind's AI Can Control Superheated Plasma Inside a Fusion Reactor. And I looked at the blog post and just thought, what the heck is going on? I do not understand any of it. A lot of these words, I know they are words, but I don't know what they actually mean. So I'll try to clarify all of this one by one. I want to start with just talking about what nuclear fusion is, what is plasma, what is this thing that they call a tokamak, and to Adrian, Thomas, Amir, feel free to jump in at any time, but I'll just get going. So the article starts out saying that DeepMind in this work has continued their streak of applying world-class AI to hard problems. So with this, in this work, it's a collaboration between DeepMind and the Swiss Plasma Center at EPFL, which is a university in Switzerland. And they managed to train together a deep RL, deep reinforcement learning algorithm to control the superheated soup, aka plasma, inside a nuclear fusion reactor. And apparently this is important because it can help physicists understand how fusion works. It can potentially speed up the arrival of this clean energy source, which apparently is an unlimited source. And I learned that nuclear fusion provides a lot of energy relative to a tiny amount of fuel or a tiny input. So it's very efficient, it's cleaner and safer than fossil fuels or any conventional nuclear power, which uses fission that separates nuclei rather than fusion, which combines nuclei. And yeah, wondering if any of the panelists or speakers, guests, could clarify anything that I just said. That would be really great.
Yeah, I can jump in. So I mean, fusion is a phenomenon in physics that we have known for decades now, and originally it was very interesting, but because it probed how we understood how nature works, very early on people caught on to this and discovered that this could be used as a source of energy, just like anything that has to do with nuclear physics. People realized that it could be implemented to extract energy and make it useful for normal daily things. And what has caught people's attention lately is the fact, well, not the fact, yes, the fact, I guess, that we are in a period of time that we are looking for cleaner sources of energy. And fusion happens to have these nice characteristics that would make it an attractive candidate to replace, if it were successful, almost everything that we have. So I guess there has been a refocusing from that side of things. Very plainly speaking, fusion just means that you are grabbing two pieces of matter and putting them together, and out of this nuclear reaction, it's not a chemical reaction, but it's a nuclear reaction, you can extract something out of it. It's a reaction that will give you something that you can use to heat water or move a paddle or something like that. So that's why it is important, and I think that this article puts the pin on it in highlighting something that is very sophisticated and a very old question. So that's why it's part of the importance of this article.
That's awesome, Adrian. Thank you. That was a great explanation and definitely helps. And one thing that I thought was interesting is that, I can't remember if I said this already, but fusion, you combine two nuclei together and the resulting mass of the single nucleus that it forms is less than the mass of the two original nuclei, and that leftover mass is energy. And this relates to Einstein's famous equation I think we've all heard. Yes, E equals mc squared, baby, as Amir just wrote in our chat, where E is energy, M is mass, C is a constant, the speed of light. So energy and mass can convert to each other. So it's very cool for me to see this equation come into play. It's kind of like in real life rather than just like what we learned or what I learned in school. So in the article title, the Technology Review blog post, they mentioned plasma. So I also have just been thinking, like, what the heck is plasma? So I learned that plasma is often referred to as the fourth state of matter, along with solid, liquid, gas that we're all familiar with. And yeah, similar to how like a liquid will become a gas when it's boiled, a gas will become a plasma. And this is important when talking about nuclear fusion because the temperatures required for nuclear fusion to occur are extremely high, so that matter would be in the form of plasma. Does that seem like my interpretation is correct?
Yeah, I think you got it quite right. I mean, the cartoon version of it is that we're trying to recreate what's happening inside the sun. We're trying to recreate those conditions such that we can get basically, if we have the right fuel, if the fuel is accessible, we can have an almost endless source of energy. We're trying to recreate a little sun on Earth, if you will.
So, it definitely takes me back to the good old physics days. So plasma has a lot of interesting properties, and normally, in order to be able to use it for various use cases, we try to control the properties of this. As you said, these little suns that we are creating, have different types of properties, and physical equations and simulations, things like that, to predict the properties of, and knobs that we have to control them. But in this particular case, they use reinforcement learning, and I want to bring in Thomas and say, what's the relevance of doing it that way?
Yeah, so my understanding, and I'm by no means an expert on the control mechanism or the tokamak, but they have a torus-shaped machine, which is like a donut-shaped machine that has a thin slice running inside it that holds the plasma. And there are 19 coils in this machine that you can put voltage through or not put voltage through, or put different pulses of voltage through, and that will produce a magnetic field that induces the plasma inside that tube into one shape or another. And so the way that that's controlled kind of before this reinforcement learning approach has actually the mechanism is very complicated, and even reading the paper the amounts I did, I can't confess that I'm an expert on how that's done, but it requires setting some parameters for how it should be controlled, then running that through a future looking generator that runs equations, and then tuning those knobs in the appropriate way for that. I think anyone can correct me if I'm wrong, but
I can actually add maybe a little bit more of context. I mean, one of the complicated things about building these instruments or having to do with plasmas is that you might be in a regime where you are no longer seeing things. Like when you optimize for something, let's say that you want to increase the speed of your car, you are able to track something outside of your car that allows you to tell, I want to go faster or slower. A lot of times when you're, for the specific case of the tokamak, people no longer see what a plasma is or what a plasma looks like, and they have to rely on other metrics to interpret what is going on. And that's part of the complication, the interpretation of is it really happening? Are we measuring the right thing? Prevents a human to understand the whole concept. And that's why it becomes complicated. Not only the fact that it's a system with a lot of parameters, but also that we're almost flying blind, if you will. You're no longer visualizing what's happening. And that's why they have to do all of these very complicated things to compensate for that.
That's really interesting, Adrian. You're clearly so knowledgeable about this. Another question I have, so for this tokamak, and Thomas, that was a really awesome explanation of what it is. So as I was doing my research, I learned that, well, I guess I'm really wondering, why do we want to control plasma within a tokamak? I did read that, so plasma, it's extremely high temperature. If the plasma touches the edge or the kind of walls of the tokamak, it'll cool down, and it could also damage the tokamak itself. So I was wondering, is this why we care so much about control, or was control more like what you were saying, Adrian, to understand the dynamics?
I think, I'm not an expert in plasma confinement, but like any other thing that tries to look like a battery, you want to create an environment where you can extract the energy over and over again. Fusion of the fuels that people think are viable for production of energy. Fusion has been observed many times in particle accelerators or in nuclear physics laboratories. But what is important is that you can have a large source of fuel that you can fusion together over and over again. And that's where the confinement is important. That's why having a tokamak is important. Making the fusion once or twice will give you little energy that might not even light a bulb. But if you want to power a city, you want to make sure that you are putting the fuel in this sophisticated battery, and that the fusion is happening over and over again, and you are able to extract that energy over and over again. And that's why fusion is important. All these complications of magnetic environments. That's why we need to have that.
So is just to confirm I understand, is tokamak essentially a very well-controlled container or environment? Like, is that literally what it is?
Yeah, it's like a magnetic bottle, if you will. The plasma is flying around without actually touching anything.
Right.
Based on the interaction of the plasma with a magnet, you're bouncing off magnetic fields, if you will, like a magnetic mirror. Because as Serena very well said, if it were to touch anything that is solid, it would just lose all its properties and it will merge there, and then you're done. It has to be flying in vacuum, bouncing around, having this, at least in my mind, is like a gooey thing. It's not really gooey, but it kind of has like that perspective of this thing rotating, flying around. Right. And that's why we have something to control it, make it sure that it doesn't fly off, that it keeps things confined. And that's, I think, where reinforcement learning comes in.
Very cool. So that was very science fiction-y, like just a bunch of matter floating in the air doing things. So DeepMind, previously used reinforcement learning based methods to solve problems that had ginormous search spaces, like AlphaGo, Minecraft, traffic, energy consumption, etc., etc. And normally, I'm not very up to date about the techniques in reinforcement learning, but from my 3,000-mile understanding of what happened was that they used reinforcement learning to significantly reduce the search space, and that's how these problems were more sufficiently solved using ML versus the traditional physical simulations that we do. Is that what's happening here as well?
Yeah, so to a large degree, the question here, let me like characterize the question one more time, is you have 19 kind of knobs that you need to turn, and those knobs control the voltage that control the shape of this plasma. The way that you know whether or not that plasma is controlled is via sensors being triggered in there that don't tell you the full shape of the plasma, but might tell you different measurements from within that thing, which is like maybe the density or the apparent density of the plasma at a particular point, or the heat within that distance. And I may be missing one of the other types of sensors from that, but you only get some measure of, you don't have like a full 3D model of what's going on in the tube. You have some sensors going on in there, like Adrian had mentioned, and you want to turn these knobs. So one of the ways that you could do that would be to look at every possible configuration of plasma that could be into that. It turns out there are an infinite number of configurations of plasma, and it's intractable to do that. So you have to reduce the search space, as Amir was talking about. The cool thing that we have here is that we have a pretty good understanding of how plasma interacts with the magnetic fields, and where they actually have modeling equations for that. And so it's possible to model very, very, very close to what actually happens if you have an actual modeled state of the plasma and a change to the voltage that's running through these elements of the tokamak. So what you can do is create a simulated environment where you have a reinforcement learning agent who is taking action in a simulated environment, and then you create what's called a reward function, which is just values associated with different states of the plasma. So one of the things is, like Adrian was talking about, how if it touches the wall, that's all you get. It's done, right? So you can assign a penalty to it touching the wall, and you can assign a more positive reward to like a particular shape. Like if you want it to maintain like a thin band all the way around, and that should be stable, you can create an incentive for it to maintain that thin band of like equal density all the way around. Even if you can't observe that happening. And so once you have those things you have a simulation, you have an objective, and you can train the agent to do that by iteration. You'd say, hey, try to do this, and then have it observe what happens, and then iterate on the approach.
Okay, cool. So I'm going to try to summarize what you said.
Yeah.
So this is essentially like the relationship between this problem and reinforcement problem. Reinforcement learning problem is that in reinforcement learning problem, we usually have an agent that, an action happens to that agent, or that agent takes an action, which results in changing the state of the agent, right? So, and normally if you have reward, and you're looking to optimize some sort of reward. So in this case, the agent is essentially parameters like magnetic field, et cetera, of, the agent is a change in those, or is that the action that is a change in, say, magnetic field? Mm-hmm. And the state is the state of the plasma, and like, what is the reward function that we're after here?
So you could think of like the agent as the robot that's turning all the dials, and it's trying to come up with the best strategy of turning all the dials given the evidence that it's getting back from the sensors in the tokamak. So that's what the agent is the right. Dial turning robot.
And what's the reward?
The reward function is like how many, like you can imagine you have this robot turning dials, and then you have a window that whenever it performs well, a hand reaches through and hands it some number of robot cookies that it loves. And so whenever it does well, it gets more robot cookies. Whenever it does poorly, it gets robot cookies taken away from it. and that's the way that it learns. It's not really robot cookies. But
What I mean in terms of the plasma is that a specific property of the plasma that we're trying to improve, and that's essentially what the reward is?
Yeah, so they in the paper, they have several criteria for the reward function. They ran different experiments over time, one of which was definitely keeping the plasma away from touching any part of the physical space. They had like huge penalties in the reward function for allowing it to do that. They also had like some temperature and density requirements of the plasma that they maintained, and then they also ran different configurations and different shapes of the plasma. So one they called a star flake, but I don't think they got into what precisely the star flake configuration is. There were at least 3 named configurations where they tried to induce the plasma into different shapes in the experiments, and they were able to do that. They were able to train a reinforcement agent to induce that plasma into different shapes.
Yeah. And I think it's also interesting that as opposed to the real experiment where you cannot actually see where the plasma is, you just have indicators. In this case, since they're training on a simulation, they have very well-defined things. I mean, this is the beauty of having the simulation, that you can go in and say, I want to find particle C at position X, and they can use that to train, even though in real life, you would never be able to use it. And that's one of the most striking things, that simulation, these researchers understand their system so well that they could rely on this to train the reinforcement learning algorithm. And apparently it worked very well. If I remember correctly, they were able to sustain as the maximum amount of confinement that they've ever seen. Exactly, so synthetic data.
Clarification question. So I'm just trying to think how we can reduce this to a problem that maybe I or other audience members might understand. So I do have a background in fluid dynamics focused on ocean flow. So my mind goes to like the heat equation, Navier-Stokes, and I'm wondering, so is the situation that the simulated data simulated using partial differential equation, similar to like heat equation or Navier-Stokes, as I mentioned, and then that's used as the training data to train a reinforcement learning agent. Is that correct? And then another question is, would we call this like a physics-informed system? Because I've heard that term thrown around recently as well.
Yeah, I think you're right, Serena, that they're using some complex magnetohydrodynamics equations. To the analogy between flow and plasma is actually quite close. There's a lot of things that we know from how things flow to understand plasma. the equations might be similar and not exactly identical, but similar to fluid dynamics. But yeah, they simulate this, and there's actually, as I read in the paper, it's probably the PhD work of one of the researchers. They have very precise simulator that they run, and from out of these results, they were able to provide the synthetic data for the algorithm. It's very cool. I thought that was very impressive that they could have that level of understanding.
So what like maybe the simplest possible example of this for everyone to be able to understand would be, so let's imagine we have a pendulum swinging, right? And what we want to do is train something to be able to push it and have it move back and forth. That's a pretty simple equation, right? And we can model it very, very well. Like we have a really good understanding of what's going on in a pendulum. And so what they're training it on is the equivalent of, I have a robot arm here that hits it with some amount of force, and how much force do I have to do that to get it to swing such and such a number of times. We can simulate the situation so well that I can train it on the simulated environment and then have an actual robot arm do the same thing in the real world.
Thomas, while I was reading that paper, I mean, I'm used to be a physicist and I used to work with feedback systems. And one of the attractive things about using, neural networks, some of the neural networks that they use, they have this nonlinear behavior. But now it occurred to me that you're constructing basically a feedback system that is nonlinear to try to control the behavior of the tokamak. Do you know how? I mean, I would rather stay with linear if I could, but then if I stay with linear, then I lose the possibility of having something more sophisticated. Do you know if there's anything within reinforcement learning that would stay within linear rather than nonlinear, away from neural networks, I guess, in principle?
Yeah, so the choice of a neural network just allows the modeling of nonlinear dynamics. It doesn't force it into nonlinear dynamics. It just allows the parameters of the model to be. You could definitely replace the neural network with, like, you could either constrain the neural network to only consider linear dynamics, or you could replace the neural network with a linear model. But you'd have a couple of constraints on that. One would be that it might not be able to converge as quickly, or maybe at all. Like it might not be able to learn to do the things that it needs to in a linear fashion. And the other one would be, I'm sorry, there's another important constraint that it slipped my mind. but you definitely could create an approach that would be similar to this, that would maintain it's all the form of the model.
Okay.
So if you're watching this video now, like the live session or later, there is a link in the that has a lot of resources. Serena, Thomas, and Adrian found a lot of interesting papers, articles, even a New Yorker article that explains fusion in very simple words. Do check those out. There are even GitHub repos you can play with for some aspects of stuff like this. So make sure you check that out and use it as a point of reference when you want to learn more about this topic. Also, if you have any questions, put them in the chat. We will definitely take them and talk about them. So we want you to be part of this conversation. So one of the interesting things is that we had Matt Taylor on one of our sessions a while ago, who talked about reinforcement learning in real world. And one of the things that he explained very well to us said that, a lot of reinforcement learning research is done in simulators, where, some sort of a game engine is, simulating the real world. A lot of things are well controlled. But the reality is that a robot that is trained in a simulator, when you put it in the real world, they're like, what's happening, right? So there are nuances that are different in the types of data that is being fed into a reinforcement learning agent in a simulator versus real world. And those nuances are enough to throw off the agent. So is something like that going on here? Or, of course, like fusion is a very hard problem. Like we've been trying to solve this problem for many, many years with a lot of, sophisticated physics model. and the fact that we don't yet have a good control mechanism, like a good feedback loop to control it, is an evidence of this problem being hard. So, like, to what extent are we concerned about real world noise throwing off a simulator like a simulated agent like this?
So for I can give a viewpoint, but I'd be interested in hearing Adrian talk a little bit about like how confident we are that these simulations of the plasma are like really have high fidelity to what's actually going on. Like how strong is that physical model? Because I can't speak to that at all. But definitely in the sim to real environment, we have a lot of advantages in this situation. One is we have a tightly controlled experimental framework. Like we know exactly what sensors are available. We know everything roughly that's going on inside this tokamak, and we know exactly what our controls do. So like that is something that allows us to control this environment so that a lot of those things aren't there. But a lot of it's going to depend on how high fidelity our physical model is.
Yeah, this is a very good question. Actually, I was very surprised that that just by providing the synthetic data, that was able to pick up almost immediately. I don't remember them being discussing that they had to fine tune anything. It seems to have worked right on the spot, because from experience, I know that when you build any type of relatively complicated experimental setup, what you think is happening in the setup is relatively far away from the ideal world. And there's a lot of tiny things that you tend to ignore or hope that you can modify after the fact. So in this case, I guess they nail it. I mean, I'm not sure how else to understand it, because these are things that are human size. These are like, imagine yourself like inside an NMR machine or one of these magnetic resonance machines. People, when they build those, they have a good idea what's happening, but I don't think they would be able to guarantee to this level of precision that it's doing the thing that their hope it's doing. But maybe they have that level of sophistication. Just to give you an idea, when you're winding a coil, having that coil shift by a millimeter or so from the specs, that will change the magnetic field profile of anything, and that will play some role on how the simulation goes. So I do not know. I was wondering if from the RL point of view, there's an averaging of the parameters that can help you overlook the fact that you don't know everything precisely, but on the average, you can get it right. And what these experimenters are measuring is more or less the average of what's happening, of course.
Yeah, can I just jump in quickly, Amir?
Yeah.
So to react to what you said, Adrian, I was thinking about my time when I did study ocean flow. And I remember finding this a bit strange, but quite a few papers that were published by my research group were around like, hey, we changed the boundary conditions to this PDE system, and now look at how small our diff is between like real measurements in the ocean and our simulated results. And I was always very surprised, and I'm still surprised with how good these models can actually be. So I would suspect that actually, yeah, this physical system and the modeling is quite accurate.
Robust, yeah.
Yeah, so I remember from my physics days that we had these neighbor lab that would get some sort of a noise at a certain time every day in their experimental devices. And for the longest time, they were tweaking all the knobs they had in the experiment. And eventually, at some point, they realized that there's a truck that passes the street at a certain time every day. I don't know what was the truck, but the vibrations from that is disturbing the system. It's introducing that noise, and you're like tweaking all the knobs, and you're like, oh. So I'm very curious to actually know. Again, like we can be very good at controlling systems, but these are extremely finicky systems. So I was working on quantum systems. They were very, very finicky. Like somebody jumping up and down in the next room, and your experimental results were different, right? So. Or somebody turns on the light or turns it off in the next room, and the electrical fluctuation through the ground comes to your so of course they are very, very well maintained and well known to a large extent environments, but still real world has noise. And I'm curious about the same question that Adrian asked. How does the training of these models deal with that kind of real world situation?
Yeah. So just like one thing about this situation that gives me some pause is, or some cause for optimism, is that the same equations that are used in the current control systems are also used in the simulation. So the current way the tokamak is controlled before this experiment, like, already relies on these equations being, like, having high fidelity. So that's one thing, is like, you couldn't control it in the world unless the simulation had some reasonable level of fidelity. But before we give it too much credit, let's talk about the process of training the reinforcement learning thing, because it definitely did not work, like, out of the box on this. What happened was they set up the simulation, and then they would train a new agent given some starting condition, and the agent would try to turn these knobs in a way, and then it would almost certainly fail really fast, and then it updated we're going to talk about the algorithm in a little bit, but I don't want to get too deep into that. But it's going to learn from each iteration. So every iteration, you can imagine it making a big mistake and then finding a way to fix it in the next iteration. It's not going to do it that quickly, but that's the process. So it failed a lot of times in simulation before it got good at it, and eventually found a process in a way of doing it called a policy, a way of controlling this that allowed it to do that. So it tried a lot through the simulation and failed a lot. It just happened to do that in a safe way in the simulation rather than in a costly way in the real world.
Thanks, Thomas. Yeah, so you said we're going to talk about the algorithm in a bit, so how about we talk about it now? So with reinforcement learning, I'm trying to remember, it's been a while since I did study it. I think there are two different types of reinforcement learning, or you can categorize it into two. So there's on policy and off policy. On policy, I think, is the sort of policy of the agent that explores is the same as the one that gets updated, whereas off policy, I believe there's the policy that gets updated, but then the exploration is its own policy. Maybe someone could clarify that first of all, and then please talk about what type of policy is used in this DeepMind work.
Mm-hmm. Yeah, so on policy is the agent is in the simulation while it's learning. It is the best way for me to think of it. Like, the way I learn is by by jumping rope or by pushing the pendulum. Off policy means I can go in, learn from pushing the pendulum, and then learn from thinking about it later, or get a big stack of these they're called trajectories or trials, like of doing that over and over. Get a big stack of those and then learn in retrospect by examining those. The way the paper puts it is, like, either what's the best way to get the best outcome, or as opposed to what's the best way, given that I've gotten the best outcome, what are the actions that were most likely to have led to that?
So is the best way, given that I've got the best outcome, that's on policy, and the other one is off policy?
Oh, sorry. On policy is what are the actions that lead to the best outcome. Okay. Off policy is, given that I've gotten to the best outcome, what are the most likely sequence of actions? Cool,
thanks.
Yeah, and in this case, they actually used a mix of those two, which was it's called MPO. It's the maximum a priori posterior optimization, which just means, hey, in retrospect, what's the best thing I could have done, right? Like that's all that sequence of things means. And it's a really cool mathematical trick that we're not going to have time to dive into, but they basically are doing both of those things at the same time and converging to the middle, and then using elements of the other estimate to perform the best optimization on the other, in a way that allows it to learn off policy and on policy simultaneously. Well, yeah, it's a really cool trick, and we have resources in the show notes that'll allow you to dig further into that.
Thomas, how novel is this combining on policy and off policy?
So the approach, this particular approach was introduced in 2018. So it's reasonably new. I mean, it's 4 years is a very long time in reinforcement learning research at this point. But yeah, it was a novel approach in 2018, and it's used in a lot of continuous control experiments. Anytime you have a dial or a slider that is the way that you're doing the control, anytime your values can take a continuous range of actions rather than like a button push, this MPO algorithm is useful. And there are variants of it for the binary control situations as well at this point. Yeah, it was very novel. There are really cool experiments. One of the things that we have in the show notes is a YouTube video that was produced with the paper that introduced this algorithm, showing the performance on a large number of different continuous control tasks, like making a human model move. Yeah, that'd be great. We can take a short look. I think it's only 2 minutes long.
All right, I'll let that play in the background as we continue talking. But I'm curious, one thing that Serena asked before, and we didn't talk about it a lot, was, if the reward function that is being used for this training physics informed. And I think we've been seeing more of that recently, because, in physical simulations, the reason that models generalize in predicting the world very well is that we build in a lot of information about this system symmetries that we know, and use those symmetries to predict the behavior of the systems better. And that's how we get, simple first principles that predict the world pretty well. Is something like that going on in constructing the reward function here? Or yeah, any comments on that?
So in the paper, the DeepMind researchers worked with the folks from the university to come up with the reward function, and they're just defining the conditions that are positive versus the conditions that are negative, and nothing about how to get there. So they're saying, the plasma touching the walls is very bad. The shape is defined as like points along the exterior surface of the shape, and how close those are to ideal within each slice of the tokamak that can be observed, and there are also 2 more related to the density and heat of the plasma, I believe.
So you mentioned the shape. Oh, sorry, Adrian, do you want to go ahead?
Yeah, I just wanted to ask something more generic about the algorithm. I mean, the flavor of the thing that this algorithm is doing, I think would be very transferable to other areas in physics where there's a lot of hyperparameters that can be tuned. Like, for example, I work in a particle accelerator, and I know the operators had a lot of knobs in their control room trying to optimize the beam that was delivered to the experimenters. And something like this would be like very good, because having people there 24 hours a day usually burns them out. Having an algorithm would definitely be something very attractive. So my question is how easy it is to transfer or to grab, the model used here for the tokamak and transfer it somewhere else where you're still tuning parameters, but the situation itself is very different, and you might not have a lot of as perfect simulations as you have here.
Yeah. It's very difficult. It's very difficult to typically, right? Like one of the things that allowed this to be a successful project was that we have a very high fidelity physical model, and we can train a very high, like there's a safe place to fail, right? The model can go in and interact with the environment in a way that is representative of how the physical system would behave in the real world, and it can learn how to do that through, you know, a lot of trial and error in a way that is applicable to the real world. So the fidelity of the model that we have to the physical environment and how it's going to behave is really, really important. That said, we can still learn things that are important and transfer those, and then do some more learning, some more or less costly learning when the failures aren't as catastrophic as they would be at the beginning of the learning phase. So there are techniques that allow that type of learning. For something like a particle accelerator, like any mistake is going to be really, really, really costly, and so there's probably a good reason that DeepMind didn't choose that one first, for example. But I agree. I think that's a great opportunity, and I think that it's very likely. If we went and talked to some DeepMind researchers right now, I'm sure there's at least a couple of them with an eye towards CERN. Yeah.
So Thomas, I'm also thinking, how cool would it be to research this stuff at DeepMind? You get to work on so many interesting problems.
Yeah, like a 25. It's really cool.
It would be. In the technology review article that talks about this DeepMind paper, there's a section of it that shows the different shapes. And I think, Thomas, you had mentioned shape earlier. And I think they write that they are able to have not just one body of plasma, but two bodies of plasma in a teardrop shape. Adrian, Thomas, or Amir, why is this important? I was sort of trying to wrap my head around why we care about it and couldn't come to any conclusions.
Yeah, it's a good question. I don't really know what's the importance of having a lot of them. I think when they start up the system, it will not be in a stable configuration, and apparently there's a few of them that can work. Some very exotic shapes like these snowflake or star-like one. I don't know if it has a particular physical significance, but I think that what they were trying to emphasize, that even the more complex situations, the algorithm was able to handle or was able to reach. That would be my reading of that particular statement. I don't truly know.
It's kind of like they're boasting, like, look how powerful we are.
Yeah,
which is pretty standard in this type of papers.
Yeah, I also read it as a kind of a flourish dunk.
Yeah.
Yeah.
One of the other interesting things is that, at least that I thought about thinking about nonlinearity in these complex systems, is that sometimes you have things that coming from chaos, bifurcation, all of those exotic things that people that do chaos like, and having not two nonlinear systems interact with each other. I didn't read anything about it. I wouldn't be surprised that they would see that they were driving the system from one place to the other. Sometimes it would split, and sometimes it would create one shape and sometimes another one. But I didn't see anything like that. It would be cool to see what were their experiences in trajectories, in creating these trajectories in the plasmas.
Very cool. So I want to quickly show you, we mentioned this a few times and I showed it, sort of flashed it on the screen, but very quickly I wanted to show the resources that we mentioned a few times. So as I said, my friends here have collected a lot of useful resources that you can use to get deeper into this topic. As you can see here, this is the recipe. The link is in the show notes again. You can take a look at it. You can see this video and rewatch it and read some of the notes about it, but also a lot of other relevant resources like the technology review and the notes that we have taken about them is also available. So feel free to take a look at that. There are a lot of resources, even some GitHub repo you can play with. I think the Amazon simulator for reinforcement learning is a relatively known one. But yeah, is there any of these topics that you want, any of these resources that you want to specifically highlight, Serena, Adrian, and Thomas? I think while you think about that, I mentioned, I think there was a New Yorker one that explains, I think was it this one, that explains, plasma and fusion in a pretty plain language. So that would be a good place to start.
Yeah,
Yeah.
the Department of Energy one, so directly above number 5345, I believe, 3 and 4. Anyways, those are very good for someone just starting out as well.
Yeah, and for the physics people, I added a resource that contains opportunities for using, not only reinforcement learning, but machine learning in general. I believe that the DOE is very interested in applying this method to basically any research topic under the umbrella of the DOE. I think that would be a good starting point to start thinking of how you can apply stuff like this.
Yeah. For the reinforcement learning or computer science folks, I'd say the maximum a posteriori policy optimization paper is really good. Tell you a lot about the internals of that and why it's novel. And then for folks who come at it from more of a code angle, the implementation in the DeepMind Acme repo is really great. That's sometimes more accessible for a lot of folks than the math. I'm one of those folks, so I go there rather than the math paper to understand a lot of that.
All right, very cool. So we're almost out of time. So I wanted to ask each of you to quickly wrap up what we've seen and what we talked about. Is this impressive for you or not? And where is this going? With a call to action, with a verdict at the end. Maybe we can go alphabetically to make it more fluid. Adrian?
This, in my opinion, this paper offers a very interesting application of a very complicated algorithm to something that has quite importance. And it's important because all of this was trained with synthetic data. There were no experiments, which reduces the cost. So this seems to indicate that if we have a good predictive model of something, we should be able to employ algorithms which applies to a lot of things in physics.
Oh, I guess it's me next. So I think it's really interesting seeing the state-of-the-art work. Number 1, state-of-the-art. Number 2, reinforcement learning. Number 3, it's applied to a real-world problem that actually has real implications that can benefit all of us. Sometimes machine learning research, I find, is sort of more like a academic pursuit, but this seems to have real-world implications. Maybe not now, but hopefully in the future with regards to climate change.
Yeah, I think that this paper is really cool. I learned a lot about the physics of nuclear plasma doing it, which is a great excuse to do that anytime. I think it shows the conditions under which the current state of the art can be applied, which kind of gives you, as we've already talked about, an idea of the types of systems that can be modeled this way, and also the next steps for the researchers of how do we bridge that sim to real gap a little more? How do you account for the differences between the simulation and the real world in a way, or make models that are robust that they can bridge that gap? Those are the things that I think are truly novel about this paper.
Very cool. So do I get it right that you're all very impressed by this work?
It's very cool.
Yeah, it's very cool.
I'm more like, I'll take everyone's word for it that it's impressive.
I'm generally very cynical about real world applications. So things like, would this actually impact climate change? That sounds like several buzzwords jammed into an article for sake of PR reasons. And I have done scientific work, and reporters have written about it, and I know that, oh my God, what are these things you're saying? That's nothing but that we did, right? So I'm gonna hold my judgment until we see more. So definitely from an academic and scientific point of view, it sounds like a very impressive piece of work, but definitely excited to see more about what other research areas that will enable an application areas. And on that topic, we have a few minutes left. So I'm going to ask each of you again to, give a call to action to our audience. What should our audience do for them to get more familiar with topics like this, or to use it? What change do you want to see in the world based on what we talked about in the past few minutes, and what should our audience do to achieve that? Who wants to go first?
I guess I can go. One. Maybe to the audience, familiarize yourself with reinforcement learning and get comfortable with it, and think about ways that it can be used for real world problems, and maybe let us know on one of our Slack channels. I think maybe the random channel could work, or unless Amir has a different idea. Okay, random channel, let us know.
Yeah, I would say that echo Serena, familiarizing yourself with reinforcement learning is as accessible as it's ever been, and it's getting more and more so all the time. There are libraries in a lot of popular frameworks, and you can just go on GitHub and search for them. I'm not going to promote any particular one because they're going to be different for everybody, which one you want to choose. But it's never been more accessible. Go out and give it a try. Try to train one of these things. You'll probably fall in love with it a lot more than you think you will.
And I would, I guess, third that opinion, especially for the physics folks out there, familiarize yourself with machine learning. In a typical physics background, don't usually touch on machine learning a lot. And speaking for experience, I think that we might be at a stage where it's okay for physicists to accept that we are at the limit of the horizon complex, that we cannot understand everything from first principles. And the tools that machine learning provides can be a good step towards achieving that goal. It's okay for you guys to say, I cannot understand everything. I'll use a little of sophisticated math to help myself.
Yeah, on that note, I remember when I was leaving physics world to join the AI world, I was a little sad that, these are different worlds. But, given especially the past few years, the work that DeepMind has been doing with protein folding, with, a lot of other interesting, science problems, simulating fluid dynamics and things like that, I'm very excited to see these, different worlds colliding. And as physicists, we always love using new, cool tools. And I'm excited to see more of that used. And yeah, so I don't want to repeat what everybody said, but I'm very excited to see what's coming up in the area of science interacting with machine learning. So that's definitely a very exciting area, and I think all of us are very, very excited about that.
Yes,
absolutely. It's like just one more point beyond that. So I think there's no reason there has to be a limit to at the interaction of these, like the contributions of machine learning to physics and physics to machine learning. I think will just accelerate one another, and so like the machine learning approaches will inform like new, deeper understandings of the physics behind some of these approaches, and vice versa. So I'm excited to see what that is. There's no reason it has to be physics or machine learning.
Both. Absolutely right.
Yeah. I definitely love that. As again, a lot of the time when tools are becoming, when techniques become tools in different fields, we do see a lot of cross-pollination. Like, physicists have been using mathematics and statistics for the longest time, probably, and they sometimes have to invent wheels that are different than the wheels that people in other fields using computer science use, because they're thinking about the problem slightly differently. I keep saying this, Serena, but we should definitely do this. I have this friend who's working on this very awesome piece where, how in convolutional neural networks, translational symmetry is built in, and that's why you get such good performance. So he's working on, how about other symmetries? Like, what if you have rotational symmetries? What if you have other pieces of group theory, like Lie algebra, like essentially marry Lie algebra and, loss functions and architectures that we're using in deep learning. So that's a super interesting topic, and we should definitely bring Nima to talk about this.
Yes.
On that topic, we're out of time, unfortunately. Thank you so much for joining us. Check out the resources we collected for you and for this show. and check out the profiles of our guests. And hope to see you next week that we're going to talk about ML ops, I believe. Awesome.
Thanks,
Thank you so
everyone.
much. Thanks, everyone.
Thank you.
Bye.
Thank you. Bye-bye.